last question was actually a great lead-in to some of the things I'll talk about in the first half of this talk. But I'm going to kind of zoom out a little bit and probably be more speculative than I should in this talk about trying to think kind of at the neuropsychological level, try to think big about what we know and what we don't know about cerebellar contributions to cognition, which Rich outlined in the beginning. And at least when we think about cerebellar contributions in humans to tasks that we generally think of as sort of the meat and potatoes of cerebellar learning, we've used things like prism adaptation and visual motor rotation, which Amanda beautifully explained right before. And when we look at patients in these tasks, again, like Amanda showed, you see this decrement in learning, this deficit in both learning and these after effects, this sort of gold standard of remapping. And you can see this in these rotation tasks. These are just example papers, but this has been replicated many times now. And we've generally thought this is just obviously a very general cartoon about what role we think the cerebellum plays in learning these kind of perturbation tasks. Okay, so some kind of internal model that is using predictions to update future movements. But as JJ just intimated here, these tasks really are, they seem so simple. They seem like these kind of dumb learning tasks, but they're actually, they recruit, as you wouldn't maybe not be surprised, they recruit a lot of different mechanisms. So Jordan Taylor, my PhD advisor, used a very high-tech method, which is just asking people what they're doing. So nice and cheap. And what you can do in these tasks is you can dissociate learning that people are aware of, so learning that we'll call explicit for simplicity here, but learning that they're aware of. So you ask them, where are you moving your hand? And they'll tell you, I'm moving my hand over here to -8, let's say. And then you impose that rotation, and then over time, what you'll actually see is people will drift, so the adaptation system doesn't care much about whether you hit the target or not, and then they'll adjust their aim downwards. So you actually create what we call a sort of visual motor illusion, where people think they're reaching at 6, they're actually reaching out here, and that's allowing them to achieve task success. Okay, so we can dissociate these two qualitative learning processes into, again, for simplicity, what I'll call implicit adaptation and sort of explicit action selection. All right? And these will sum up to the actual observed behavior, the observed movement. So this is just, you can just subtract this blue one from this purple one and get this red one. Okay, so when we first thought about this, we said, all right, well, clearly this red process is the thing that patients with cerebellar pathology would show deficits in. But then the question is, well, could they also be bad at this blue process? We don't know. Maybe that's what's been driving some of the previous neuropsychological results in those individuals. And then, of course, another question could be, well, maybe they're impaired in both. So these are the three, we'll say these are the three sort of possible explanations for the deficit in patients with cerebellar pathology. And actually, a recent paper from Peter Butcher that he did with Jordan suggests that it's the answer to both. And I'll just show you the data from that paper. So if you look at the learning curve, again, this is just the movement angle in the task. Okay, so the goal of the task is to reach 45 degrees offset from the target. Control subjects do pretty well and have a fast learning rate and asymptote somewhere near the solution, but patients have a slow learning rate and seem to kind of under-asymptote, let's say. And if you dissociate this learning curve into those implicit and explicit curves, as predicted, you can see the cerebellar patients barely show this implicit adaptation. Okay, it's subtle, but it's much less than controls. These are 95% confidence intervals for reference. And then finally, what's really surprising and I think pretty cool is that if you look at this explicit learning process, you also see a similar deficit. And it's consistent in that cerebellar patients seem to under-aim. They volitionally usually do something. They understand that they should reach in another direction, but they underestimate that angle. And again, this is explicitly, this is presumably a sort of at the cognitive strategy level of the task. So this kind of says, well, this maybe still is right, but maybe this is kind of like this forward model we've talked about, maybe you could say is kind of also like a cognitive forward model. That would be one speculation. But really, if you want to make any interpretations of the results I just showed you, we have to first try to deconstruct this explicit learning thing. What the hell am I actually talking about? Are people like magically come to the solution, or is there some sort of psychological mechanism that we can pick apart? And the prediction we had, based on a little bit of previous research, was that people are actually performing some kind of mental rotation. Okay, and the phrase mental rotation, as some of you might know, is we didn't make it up. It's actually from a very classic paper that I consider one of the sort of important points in what we'll call the cognitive revolution. I actually like to ask this. How many people here, raise your hand, are familiar with this paper? Okay, maybe like 40%. Yeah, that seems about right. So for the other 60%, I might ask you to quickly perform the task, okay? So I want you to tell me if these two symbols are the same shape, just rotated, or are different shapes. Raise your hand if they're the same. Okay? Now these two shapes, raise your hand if they're the same or different. Same. Raise your hand. Good, okay, I can't measure your RT there, right? But it turns out that there's a beautiful result, which is, this is published in Science in the early 70s, which is that the magnitude of rotation you have to perform to do the matching task, the same different task, linearly predicts your reaction time. All right, and the interpretation that Roger Shepard and Jackie Metzler had was that people might be performing some kind of true mental rotation. There's some representational space that they're working this object through. And so we thought, well, maybe this could also explain the kind of strategy people do in this goofy task that we do in the lab, and that would be some kind of visual, we'll call it a visual motor mental rotation instead of a visual mental rotation. And maybe these things are somewhat analogous, okay? And so the way we tested this was we had people do this rotation task that Amanda and myself described before, but they do it in these iterative pairs of trials, okay? So on a first trial, they'll reach to a target and get some kind of perturbation, so rotation of that size. And then on the immediate following trial, the target will actually appear somewhere else, and then they'll have one chance, one-shot learning to remember this rotation and then apply the right strategy to counter it. Okay? And what we do here is important is we actually also delay the feedback so we kill that implicit adaptation system. As Court suggested, right, the time interval really matters for that cerebellum-driven learning, computer-driven learning. Okay, now what we see is if we change the magnitude of the rotation on this trial, and then we measure the reaction time on the following trial, we get this linear function. Okay, so it really looks a lot like what we see with this kind of abstract visual task, but now in the domain of replanning a movement relative to a target, which we thought was pretty nifty. But, you know, this is one way to do the task, right? This is the kind of, you'd imagine the sort of heavy cognitive lifting where you actually compute the explicit solution to the task. But you could also imagine that why can't you just learn a stimulus response map, right? Maybe you could just learn maybe through a reinforcement mechanism or even just simple kind of item-based working memory. You just remember when that target's there, I should move my hand over here. So these are both, to me, reasonable ways to do this task. And you could say, in the language of cognitive psychology, which is where I come from, that this would be a sort of algorithmic solution to the task, and this would be kind of a stimulus response or maybe caching of a solution relative to a visual stimulus. And so what we did is we did a classic manipulation, which is just a 2x2, and we crossed what we consider to be the two important dimensions of the task. One here being the magnitude of the rotation, the thing that would modulate reaction time predictably if you're doing mental rotation. And one would be the number of items you have to remember. So if you were doing a stimulus response strategy, this would be an important manipulation, right? It would be much harder to remember 12 SR pairs than just 2. And I'll go through this quickly, but this is all in healthy subjects. If you plot the reaction time curves, you can see that in the simplest case, where you have only two targets and a small rotation, your reaction time briefly comes up in the beginning and then drifts down to under baseline, actually. Then if you look in the condition where I just increase the rotation size, but give you the same number of stimulus response pairs, early on you see a dissociation of the reaction times, and then they meet. Then if I give you a situation where it's the small rotation, but the large number of targets you have to learn about, the reaction time looks very similar to the two-target condition early in learning, but then is elevated relative to that condition late in learning. And finally, in the hardest case, I give you the largest rotation and the largest map, stimulus response map. And early on, your RTs look like the two-target 75-degree condition, but then they stay elevated. And just to summarize this kind of confusing plot, essentially what I think it shows is that early in learning, we see evidence of mental rotation, where the main effect is the size of the rotation on your reaction time. That's the classic mental rotation dissociation. And then late in learning, we see a combination of people still doing this algorithmic strategy, and then in the simplest cases, people have now learned a stimulus response map, and the RT differences go away. So the key variable, we think, dissociating these two strategies, at least in the length task that we do, is the size of what I'll call this SR, stimulus response map. Okay? And you could imagine this being above working memory capacity, which I would say anything more than 4 about, or below it, or within it. And so what we did is we returned to this task with the cerebellar patients, where they had to learn this rotation. Now this exact experiment was done over 8 targets, so something we would consider pushing you more towards this algorithmic strategy. And we just did the same task, but now with just 1 target. Okay, so this is the task here, with 1 target. And as you can see, the deficit in the patients goes away. So they can learn the task when it's a simple stimulus response learning. The patients look as fast as the controls and asymptote at around the same value. So this suggests that maybe, at least in humans in this kind of setting, pathology of the cerebellum doesn't play a huge role in very simple stimulus response learning, but might actually be playing, in this case, it might be playing more of a role in this algorithmic computation. Again, this is all removing the implicit learning, so we know it plays a role there. So this to take stock, we're saying individuals with cerebellar pathology show learning deficits in these tasks. Okay, but we can break these tasks down into 2 processes. And then we can show that they show deficits in both of those processes. We can also further break down this cognitive strategy or explicit process into its own 2 processes, and then trying to suggest that cerebellar patients have issues with this algorithmic computation, the smooth movement of something in mind, let's say, rather than this stimulus response. So the question then is, if I think this behavior is something like this behavior, and I think cerebellar patients have an issue with this behavior, then logically they should have an issue with this behavior, even though there's no overt movement planning in this task. So that's what we did. This was a paper that we used as kind of inspiration that pretty much just showed if you have people do mental rotation in a brain scanner, and Jorn Dietrichson's group has shown similar results, you do get reliable cerebellar activation. So at least there's some foundational correlative evidence that we might see something. So we did the very classic mental rotation task, this time with letters, and people just have to do a judgment of whether this R is a reflected R or a normal R. Okay? Then they make a response on a keyboard. We measure the reaction time before the response, and we do that iteratively over many trials. And we also wanted to control for just kind of general working memory difficulty or processing. Maybe there's a general deficit, and a deficit in this task doesn't reflect anything special. And so we also had them do what's called this working memory search task. Okay, where you give people a sequence of images of varying lengths, in this case 1 to 5. They have to maintain that sequence, then you probe them on a new stimulus, and they have to judge if that new stimulus was in this sequence or not. Okay? So this would be a rejection trial, and you measure the reaction time there as well. So you have 2 parametric variables, the length of the sequence here and a degree of rotation here. You're measuring reaction time effects relative to those 2 parametric variables. And sure enough, what we saw in the patients is that their slope, so in this sense, the number of degrees per millisecond that they rotate is slower than controls, reliably slower than controls. Okay, so something's being disrupted in mental rotation to make them slower consistently than the age-matched control subjects. And importantly, in that search task, they are not different from controls. They're actually a little bit faster, which is kind of odd. But these are for intervals taken over all subjects, so I'm not normalizing our T at all. So all of these things are significant. So we did get the main effects of the parametric manipulation, but we got this interaction there. And this, I think, it looks similar to what you'd expect from this paper here. If you're slower at mental rotation, you're more likely to under-aim, especially if you feel some urgency to get through the task, which we think everyone sort of does to some extent. So we think this might say that there's a kind of general cognitive issue with doing this smooth manipulation that could affect both of these tasks. And now I'm going to speculate a little bit. There's a kind of, I think, compelling but somewhat vague idea out there about cerebellar patients having dysmetria of thought. So we know they have dysmetria of movement, as Amanda showed. We know that movements that we could make relatively straight, they make in pieces or they overshoot or undershoot. So there's this dysmetria effect. Maybe something going on, I'm not saying this is like the phenomenological experience of the patient, but you could imagine that something that would increase the RT is a sort of dysmetria of like a mental operation. Okay, that's the speculation. And so a future direction is to say, all right, if you have this algorithmic computation that I showed you there's a deficit in, are there another set, if we look through cognitive psychology, are there other experiments we can do with different kind of smooth parametric mental operations and try to see if we can build greater evidence that cerebellar patients have a general deficit in these kind of operations. And one thing we're starting to look at, arithmetic computation. So again, in the cognitive psychology literature, these are sort of there's a sort of nice dissociation here between operations you do parametrically on a mental number line. So if you're doing 27 minus 13 right now, you're probably using some kind of spatial representation. If I ask you what's 1 plus 1, that's probably just sitting in your rote memory, right? You don't need to do an operation for that, just retrieval. And actually, this is a preliminary data in I think a dozen patients and about half the number of controls. But we do see that even if you correct for baseline RT, which I'm not doing here, patients show this increased slope when they're doing these mental number line computations. But then when they just have to perform what's called ties, so 2 plus 2, 3 plus 3, 4 plus 4, these rote memory things where you don't do any computation, they don't show a slope difference. They don't show a slope at all, and neither do the controls. So at least this is preliminary evidence for another sort of parametric mental operation. No overt movements are being recorded here. This is the reaction time before the movement is initiated. So no overt movements, but a clear kind of process difference. And then just to kind of give a final sort of future direction thing, this is a really beautiful image from a paper from Nate King and also Rich and Yorn, showing how you can look at a kind of functional map of the cerebellum where people perform a variety of cognitive tasks. And as you can see, there's kind of widespread and somewhat ordered activity. So this is a kind of data-driven approach to looking at cerebellar function and cognition. And I think maybe we can take these kind of old school hypothesis-driven experiments that I showed you here, and hopefully maybe try to get bigger samples of patients, perhaps online using tools like Mechanical Turk, and try to maybe build up a similar functional data set that's just using a variety of behavioral tasks on patient groups. And with that, I just want to thank my PhD advisor, Jordan, one of my 2 postdoc advisors, Rich Ivory, and other people in the Ivy Lab that helped. And then I'm going to end with a little advertisement, which is that in a year, we're starting a lab at Yale Psychology. So if anyone's interested in doing this kind of behavioral, cognitive, psychological work, and also some brain imaging, please send me an email at this address. I'm looking for postdocs and lab techs in particular. Okay, thanks.